Well, thank you for coming, everyone. Welcome. I know there's a tough competition out there, so really I appreciate you coming. I hope you're enjoying NDC so far. My name is Sasha, and we'll be talking about hardware performance, how to squeeze the most out of your CPU by performing some rather low-level optimizations. This is a talk for .NET developers generally. Most of my examples are going to be in C# and using some libraries which have only recently become available to .NET developers. However, the concepts described here are relevant for everyone building software on Intel CPUs. A lot of the examples are very general, and you can apply them in other languages as well. In fact, the lower level the language, the better. For example, in C or C++, it would be a lot easier to apply a lot of these ideas. But again, this is .NET. It's going to be the examples are going to be using .NET. So roughly, what we're going to do is talk about how modern CPUs are built. I'm going to spend a few minutes on this because it's really hard to understand what the optimizations are about if you don't really know exactly how the CPU is constructed internally, what the different pieces in the pipeline are, which will be taken advantage of. We'll see some basic examples based on internet questions on these different aspects of CPU architecture. And then we'll move to the actual techniques, applying what we sort of learned about the CPU to optimizing specific algorithms. Hopefully, all the examples are going to be fairly real world. I'm not saying you can take this code and apply it today in each of your applications, but it's not complete pure theory which you never will apply. It's actual algorithms used in a lot of computational frameworks, a lot of libraries, a lot of applications today. And towards the end, we'll maybe touch a little on where I see the future of optimizing this kind of low-level CPU work on other platforms. So this is a modern processor. In fact, there's two processors here. On the left is a pretty standard desktop issue processor that a lot of you probably have or had in the past. It's from the i series, the Intel i5, i7 series. It's not a very expensive processor, probably goes for $200, $300, $400. And it's pretty easy to see there's some structure here, some well-delineated pieces. So for example, this processor has 4 cores, and each core has a little piece of cache. And there's also this whole unit on the side, which contains graphics and a bunch of other things that are today built into processors. And there's a large piece here, which is the shared cache. So a lot of parts clearly visible. And then on the right, there is a somewhat bigger chip, a chip that's also a lot more expensive. This is Intel's Knights Landing, which was released a few months ago. It goes for a few $1,000s, but it has up to 72 cores. And this is today. This is a few months ago. It's not like these supercomputers that you heard about in the movies, which would cost millions of dollars to build. This is a 72-core chip, which can run your OS. In the past, Intel would make these chips which couldn't run an operating system. You would have to attach them to an existing computer that would already run some other OS. But as of Knights Landing, you can actually run your Windows or Linux on this chip directly and use it for computation. It has a bunch of cache, it has a bunch of embedded fast memory, and it can attach to additional external memory up to terabytes and terabytes of additional RAM for this monster unit to use. 72 cores for a few $1,000s is a pretty good bargain, I'd say. And people are starting to use these for financial work, for image processing, for video processing, for a bunch of CPU-intensive tasks. And then the challenge is really to squeeze the most out of this thing you paid a lot of money to get. And squeezing the maximum out of this thing applies on each core individually. So you want the maximum performance of each of these 72 cores, but you also want parallelization to work well. You want these cores to work together and distribute the load as equally as you can between them. So there's a bunch of talks we could do on each of these aspects. Today we're going to focus more on extracting the most out of each individual core. Parallelization is a whole different topic, and hopefully you've heard some talks about using parallel code in .NET and other languages in the past. But getting the most out of a single CPU is a bit more challenging. So processor organization, just briefly, I want to touch on what happens inside Intel processors for quite a while now. This general structure hasn't changed since Nehalem, which was released like 8 or 9 years ago. This is the first generation Intel I series processor. So roughly, there's two parts here. Everything here on the left is the front end of the processor, and then this thing here is the back end of the processor. And essentially, the back end is where instructions actually get executed. This is where you add numbers, and you multiply them, and you write stuff out to registers and to memory. And the front end is where roughly instructions are being decoded, processed, and rearranged. So I'm not going to touch on every single aspect of this, just a few highlights. Before the processor can actually execute any instructions, it has to read them from memory. So it all starts with the instruction cache, where the most recently accessed instructions are stored. So if you have a loop, for example, you would benefit from the fact you already read these instructions from memory, so you can just reuse what you already read. Once you've read them from memory, once you've read them from memory, you have to decode them. You actually have to convert them as well to an internal format that the CPU uses called micro-ops, uops. This is totally different from what you see in Visual Studio when you open the disassembly window. The instructions you see there are the official public instruction set. However, internally, the CPU uses a slightly different representation where each assembly instruction is broken down into much smaller pieces. So, for example, an instruction that reads a value from memory and adds another number to it and stores the result to some other location might be broken into 3 parts. Read from memory, add a number, and then write the result somewhere. And these micro-ops are then passed forward to the backend, which actually executes them. And in the backend, we have multiple execution units, or execution ports, which are capable of doing things at once, concurrently, in parallel, on a single core, right? We're talking about just one individual core here, so this is not multi-core, this is on a single core. You have multiple ports capable of doing things at once. For example, and I'll show you some more detail soon, you have a port for adding numbers, and you have a different port for storing values into memory. So if you have 2 operations to perform, if you have to add numbers and store a result to memory, and you can run them at the same time, they can actually execute concurrently inside the processor. So you can get some more concurrency out of the CPU on a single core by arranging stuff such that all of these execution units are busy at once. So here's some of the more important execution units. Currently, we have a total of 7 ports. Some of them are not really interesting. They just are reserved for reading from memory or writing into memory or doing calculations on addresses. The ones that have stuff inside are the ones that perform actual computation. So for example, we have port 0, which is responsible for things such as branching and arithmetic and string operations and multiplication and even AES encryption, which is something Intel processors were able to do for quite some time now, for a couple of releases back. Port number 1 does arithmetic as well, and also multiplication and also encryption and also floating point operations. And it turns out that even the same kind of thing, like adding numbers or multiplying numbers, you can actually do concurrently on the chip because you have multiple ports that can do the same thing. So for example, port 5, port 1, and port 0 are all capable of adding integers together. So if you have a lot of integers that you have to add together, and you have a lot of instructions just adding integers, you can actually do 3 of them at once. Your single core can execute 3 of these instructions at once. And this is very important for understanding where like the best case performance for your code is. And I'll show you a couple of examples and how we can appreciate that in advance, try to figure out what the best case performance can be for doing a certain kind of thing, and how to use these ports at once if we can. Now, Intel have this process where by understanding how the processor works, you can look at every single CPU cycle, so several billion times per second. You can look at what's happening inside the CPU and try to put it in 4 buckets, what's happening right now. And it's just a very basic flowchart. So it starts from, was an additional micro-operation allocated for execution? So basically, did the backend receive another operation for execution? Did an instruction start to execute? Now, if yes, there are essentially two options for how that happened. One is that an existing operation completed successfully. It's called retirement in Intel parlance. So if you have an instruction retired successfully, it means everything is fine. You finished an instruction, you're starting another instruction. This is the bucket we want to be in. Or an operation might not have retired, even though a new operation was beginning to execute. And this would happen if you tried to predict what's necessary to execute, but in fact it was the wrong prediction. It was bad speculation. And we'll see where bad speculation comes in the next example I'm going to show you. So this is not very good. It means the CPU is trying to foresee the future and fails. Next, if a micro-op was not retired, then, if a micro-op was not allocated, then we ask why. And then there's two options. Is it a back-end stall or a front-end stall? So one thing that could happen, again going back to this diagram, is that your back-end is busy. All ports are busy, so you can't put any additional operations in flight. And the other option is, no, the back-end is not busy, but your front-end isn't capable of pushing more instructions through the pipeline. So for example, you might have cache misses on the instruction cache. You're trying to read an instruction from memory, and you're just waiting for that instruction to arrive, so you have nothing to do in the meantime. So there's 4 buckets that you could be in. This is the good bucket to be in when I'm retiring, completing instructions. And if you're not there all the time, and no one is there 100% of the time, you can start analyzing why. You can start analyzing why I'm speculating badly, or why is my backend so busy, or why is my frontend not capable of giving me more work to do. And this is the Intel top-down process, which they stress in all their tools. This is how you're supposed to analyze performance methodically. We don't have time to do this kind of analysis for most of my examples, so you're just going to have to assume that we sort of did, and now we're just attacking the problem as we identified it. But this is the process to do. So let's start with a couple of examples that illustrate the way the CPU works. These are just highlights, and then I'll have some examples with actual code that we're going to look at it in more detail. So this is a Stack Overflow question with an astounding 16K upvotes and almost 8,000 stars. And I bet some of you have seen this before. Could you raise your hand if you did? Okay, awesome. So why is it faster to process a sorted array than an unsorted array? Here's some code. I don't understand what's happening. Indeed, if you look at the 2 code snippets, this is what you see. It's essentially the same code, which goes over an array of numbers and adds together all the numbers greater than or equal to 128. Now, in the first case, the array is called sorted, and in the other case, it's called unsorted. And that reflects reality. The sorted one is sorted. And it turns out that going through the sorted array takes 18-something time units, and the unsorted array takes 121. This is not from the Stack Overflow question. This is from an actual benchmark I executed. At the end of the talk, I have a GitHub repo link where you can reproduce all of this. So it's 6 times faster, or even a little more, to go through the sorted array than the unsorted one. And there is just one explanation for this, which has to do with branch prediction. It has to do with the CPU's ability to figure out what the next instruction is going to be. And whenever you see a branch, it's incredibly important for the processor to make a good prediction. Whenever the processor sees a branch, it tries to guess what the result, what the outcome of that branch is going to be, of the conditional check. And so in the sorted array, just think about it. Once we start making a certain branch, we're never going to stop. So we go through the array. Once we reach 128, we're always going to take the same branch. And before we reached 128, we were always taking the same branch. So there's just one inflection point where we change our mind, but otherwise the CPU should be fairly easily able to figure out the pattern and just start guessing correctly every single time. So the CPU can speculate and start executing additional instructions, even more than one ahead, and it never fails, almost never fails. Whereas in the unsorted case, we really have no idea what the pattern is going to be. The data could be totally random numbers, in any range, and then we could make a guess. It would work, it wouldn't work, there's really no way to know, and the processor keeps doing unnecessary work, never being able to progress a lot of elements at once before this information is known, before we actually know what the result of the branch is going to be. And this is an incredible result, this amazing difference between going through a sorted array and an unsorted one is really only explained by this phenomenon where the CPU tries to speculate, and if it speculates correctly, you gain a lot of performance, and if it doesn't, you lose a lot of performance. So that's just one demonstration. Like I said, we'll have some more sophisticated examples coming up later. Another example which I wanted to share with you has to do with this concept of using the CPU's execution units more effectively, which I talked about earlier. So the top loop over here is a very simple implementation of min-max. So you have an array of numbers, and you want to find the minimum and the maximum values at once, going through the whole thing just once. So this is really nothing to see here. And then some efficient developer decided to optimize this thing and sort of rewrite the code so that maybe more execution units in the CPU would be able to do some work at the same time. Now what happens here is that essentially we go through the array 2 elements at a time, and we keep 2 counters for the minimum values and 2 counters for the maximum values. So we basically go over the even and odd elements separately. And then at the end, we just figure out which was the biggest and which was the smallest of these 2 minimums and maximums we found. And this is supposedly might be better, right? Maybe, because in theory, there's more work for the CPU to do in each iteration. So there's potentially fewer branches and better chances of predicting what's supposed to happen. Unfortunately, it is slower, the optimized version. And not by 1 or 2%, it is considerably slower. And so you might be saying, okay, well, this is just all garbage, and you really can't figure out what the CPU is doing, and it's worthless, this whole thing, let's go home. And then you look at the actual generated program, at least what the C# compiler plus the .NET just-in-time compiler generated from this actual benchmark. And so if you see the simple loop, the first one, it's assembly language, but it's very, very short and simple to understand. It's basically comparing and then branching, comparing and branching to find the minimum and maximum, update them, and move on to the next iteration. The whole thing is pretty small, and Intel processors have a dedicated optimization for loops that are particularly small. There's a thing called loop stream detector, which if it sees that you have a loop fewer than a certain number of micro-ops, some special sauce magic kicks in and makes things even faster. I know this is not a very formal explanation, but this is sort of what happens. Whereas the optimized version is, one, a lot bigger and more difficult to understand maybe, which again sort of prohibits the loop stream detector from taking place, but also the red pieces here are range checks. Essentially, the just-in-time compiler couldn't figure out in this example that my array accesses here, 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 and here are safe, and that I'm not stepping outside the bounds of that array. And since it wasn't able to figure that out, and indeed these accesses might not be safe, the I+1s might not be safe and within the bounds of the array, there are range checks here which would throw an exception if I step out of bounds. But obviously the checks have a cost, even if I'm not actually stepping out of bounds, and that slows things up. So it's not just the shorter code, the shorter loops, it is also these range checks which would happen in the optimized case. So this is just another anecdote of trying to optimize for something you think about the CPU and failing. There's also an important lesson to be learned here. A final example before we actually dive into the more serious optimization work. This is vectorization. So on top you see the same min-max algorithm, which just works on a single int at a time, and then a vectorized version, which uses vector instructions, and I'll explain what vector instructions are shortly. And this version, that's the important result, this version works in 1/5 of the time. So it's 5 times faster to do this and calculate the minimum and maximum values than to do this. And this is on a single CPU, this is on a single core, there is no parallelization, there's no multiple threads. It's just somehow magically squeezing out more from the same execution units we have on a single core. Whereas, similarly, we could have just parallelized the whole thing. So we could have taken the original loop with the min and max, and we could have used something like parallel 4 to create multiple threads, which would run on multiple cores, and that would also speed things up, hopefully. And the lovely thing is you can combine both effects. I do not have a benchmark here for this, but if you look at the results, by using vector instructions, we speed the things up by roughly 5, and by using parallelization without vector instructions, we speed the things up by about 2.5. And hopefully, if we apply both vectorization here and parallelization over here, we could get a nice avalanche effect. And we'll see, indeed, in some cases, we will. So that was just the exposition, different facets of the processor we might be trying to take advantage of. So the branch prediction mechanisms, what happens inside the CPU's execution units, trying to have them run at once, vectorization, parallelization, a bunch of things we'll be looking at concrete examples of in the next 30, 40 minutes. All right, so we'll start with vectorization, because indeed it's one of the key things Intel have been stressing for a few years now, trying to tell people, you understand parallelization, you understand how to write multi-core programs, this is all well, this is all fun, but you really have to understand what's happening in a single core, and you have to speed things up there before you move to additional cores and parallelize. So essentially, Intel processors have had for many years, since the very beginning, classic instructions, as I call them here, which operate on single values, like a single float, or maybe 2 floats, or maybe 2 ints, that kind of thing. Some examples. This instruction here, add, adds 2 integers together. This instruction here, move, copies a single integer to another location. This instruction, fmul, multiplies 2 floating point numbers. That's the kind of thing you expect CPU instructions to do, right? That's what you learn when you learn assembly language. SIMD, or single instruction multiple data, are instructions that Intel have had for like 15 years now, and again have been stressing more recently because a lot of advances have been made in the last few years. And SIMD instructions operate on multiple values at once, multiple elements, multiple ints or floats, what have you. Examples. Add PS is an instruction that adds 4 floats to another 4 floats and produces 4 results. So it does an element-wise add of a tuple of 4 floats and another tuple of 4 floats, producing a tuple of 4 results. Which is pretty nice for a single instruction, assuming it works as fast as the standard add, which we'll see later. And then you have something like vmul PS, which is an instruction that multiplies 8 floats by 8 floats, producing 8 floating point results. And in very recent Intel CPUs, like the Knights Landing I've shown you, they also have instructions operating on 16 floats and 16 floats, producing 16 floating point results. If you work with doubles, it's obviously half the size. So for example, there is a vmul instruction that works on doubles, and it takes a tuple of 4 doubles and another 4 doubles and produces 4 products, 4 double products. So these are pretty cool instructions, and there's hundreds of them. Here's a list of categories. It's definitely not a list of instructions, just some of the things you have instructions for. So obviously, basic operations, add, multiply, shift operations. Compare is pretty important, and we'll use that a little later, comparing large regions of memory. Conversions. Surprisingly, converting ints to floats and vice versa is a pretty expensive thing to do. I've seen code where 20, 30, 40% of the time is spent converting. So if you can speed that up, it's pretty useful. Cryptography, including hashing as well, CRC, checksums, that kind of thing. Various math functions like exponentiation, trig, that kind of thing. memory operations, reading and writing to memory, and finally string operations as well, like searching in a string. That's something we're going to explore a little later. Now, there's really a great variety of these instructions available in modern processors, and the question is, why is it even worth the effort? So I have the add PS, which operates on multiple values at once. Is it faster than just doing several of these classic instructions one after the other? So hopefully you realize the answer is yes, but I still do have to convince you in some way. So when looking at instruction performance, we typically look at two aspects. One is latency, which is time from start to finish. You start executing the instruction, how soon is the result going to be available? And the other aspect is throughput. And that's a little trickier to explain. So let's start with latency. Here I'm looking at two instructions, add, which adds a pair of integers, and PADDD, which adds tuples of 4 integers each. So it does 4 times the work. It adds 4 pairs of ints instead of just one pair of ints. In terms of latency, start to finish, both take 1 cycle, which is pretty cool. You can do in 1 cycle what you would need 4 instructions in if you weren't using SIMD. Throughput, on the other hand, is a little trickier, and throughput has to do with the CPU's ability to execute multiple instructions of the same kind at once. Remember, we have multiple execution units. If we have multiple units capable of doing the same thing, we can actually issue multiple instructions in a single cycle. So what could happen is that in the period of a single cycle, I could have multiple instructions completing because I have multiple units where they could be executing. So if I have a constant flow of add instructions going into the processor because I have a lot of data, a lot of numbers to add, I can actually finish 3 adds in a single cycle by multiplexing them. And so the throughput for add, if you have a lot of adds, is 3 per cycle, which is very impressive. The throughput for PADDD is just 2 per cycle, but it does 4 times more work. So it's still worth it to use the vector version rather than the classic scalar one. And this is the key lesson to learn about vector operations. They are usually as fast or close to the non-vector counterpart, but they do 4 times, 8 times, and sometimes 16 times as much work, which means you typically can squeeze out of a single core 4 times, 8 times, 16 times more operations if you use vector instructions. Now here's an example of how to actually apply this in .NET, in C# to a real practical, interesting problem. I know it's a little theoretical, but it's an algorithm that's at the heart of a lot of stuff, a lot of libraries, image processing, a bunch of machine learning algorithms, lots and lots of stuff uses matrix multiplication, and it's the classic example for vector operations, so this is the one I'm going to start with, but I have several more interesting examples coming up later. So here's just naive matrix multiplication. I have 3 of them. A, B, and C, and assume for a moment they're all the same size, just to simplify. So what happens is I have 3 loops, and the core of the inner loop is this. It multiplies 2 values from A and B and puts the result in C, which is the output matrix. The vectorized version looks like this. I still have 3 nested loops, 4, 4, 4, I, K, and J. But instead of multiplying and adding just floats, I'm working with a type called vector of float, which is a new type that Microsoft introduced with .NET 4.6. It is part of a NuGet package called System Numerics Vectors, which, again, it's been available for over a year now, but it's still not as popular as I would like it to be. And it gives you, from C# programs, access to vector instructions, which was not available before. You could do this in C or C++. If you wanted to do this from pure C#, you couldn't. You just had to do interop and talk to some native code. So basically, this vector type represents the biggest chunk of floats that your processor is capable of operating on. So on some processors, particularly older ones, vector of float would only have room for 4 floats. But on newer processors, it might have room for 8 floats. and in some very recent processors for 16 floats, and maybe in some future processor for 32 floats. The key part is you don't care. You just work with this vector of float type, which also has a size. You can read here, vector of float.count is a static property that tells you just how many floats would fit in a vector of float. And so all your operations are now going to be using vector of float. So I read from A, and I read from B, and I read from C, and then here's the actual work, multiplying and adding vectors rather than scalar single floats. And what happens in this single line is that I'm multiplying and adding 4 tuple floats or 8 tuple floats. Again, it all depends on my actual processor at runtime. When I write this C# program, I do not commit to the actual processor, which is again pretty cool because if you do use C or C++, you typically would compile your code on a certain platform and you would get code which would execute only on these processors. So with this system numerics vectors support in .NET, you can actually run code that would be sort of flexible and work on different vector sizes, different processor generations. Is it worth anything in terms of speed? So here are the benchmark results. It's roughly 5.5 times faster on the core I measured it on, which is just a plain standard Intel i7, nothing fancy, definitely not a 72-core monster. It's a $300 processor. So this is pretty impressive, speeding up matrix multiplication, which is such a core operation in a lot of algorithms, by just using some slightly different API for multiplying and adding numbers, which are pretty fundamental operations. Turns out you can do them a lot faster if you have a lot of numbers to multiply and to add. So all of this code, as I said, is available online, which you can test later as well. In the meantime, take a look at something Intel has apparently been working on. So this is from sort of rumors, but substantiated rumors from online. Intel is supposedly going to add an instruction with this lovely name, v4fmaddps, in some future generation Intel processor. And it's going to have the following, so to say, syntax, where you would give it something called ZMM0, which, for example, in our case, could be 16 floats, a tuple of 16 floats. You would also give it 4 tuples of 16 floats, so a total of 64 floats in here and 16 floats in there. And you would give it a memory location. And then what it does is described here. This is all just one instruction. This is what it does. And I mean, don't really follow the whole thing, but look at what happens here. It multiplies something from here by something read from memory and adds the result to this one here. And then it goes on and reads from another memory location and again multiplies something from here by that value from memory and adds that to this one here. And it repeats this whole thing 4 times. And this looks suspiciously like matrix multiplication, like the core of that inner loop over here, which adds and then, multiplies and then adds. This is what this instruction probably is intended for. So Intel is going to apparently add an instruction with just one obvious design goal to make matrix multiplication faster, because it is so important. And in this case, it would make matrix multiplication a lot faster because you would be able to avoid certain memory accesses as well, to more efficient memory accesses. So this is potentially going to speed up matrix multiplication even more. So Intel is working on their side of the problem by adding even more clever instructions, and we have to work on our side, which is applying these instructions, actually using them for our work. So I'm going to show you a couple more examples of using vectorization, and then some examples from different domains as well. So here's a problem, which is again interesting in certain areas. It's sort of confusing because the problem is vector normalization, and we are going to vectorize vector normalization. But whatever. What we're trying to do is we have a collection of 3D vectors, a collection of points in 3-dimensional space. And what we're trying to do is normalize them by dividing each component of the point, the x, y, and z, by the norm of that vector. So basically, this is called normalization. This is what we're doing. And the calculation is pretty simple. You multiply a bunch of things, you take the square root, and then you divide the x, the y, and the z by that norm This is what you do in each iteration over a bunch of points. All right, so here's the vectorized version. And this one actually takes a little work because the way the data is represented over here is essentially tuples of x, y, and z. But the operations I want to vectorize are going to go over all the x's and all the y's and all the z's. So it's actually going to be easier if instead of an array of points, I had 3 arrays of x's, y's, and z's. 3 arrays instead of an array of structures that has 3 components, where each structure has 3 components. So once you do this refactoring, and you have x's, y's, and z's instead of a single array, you can vectorize the whole thing pretty easily. You read the x's, you read the y's, you read the z's, and each of these, x, y, and z, is not a single float, it's a bunch of floats, and then you can multiply them like floats, and you can extract the square root like floats, but this is all vectors, this is all tuples of floats, and then you can divide the x, the y, and the z by that calculated result, which is still a vector, these are vectors, and then you can copy the results back to the arrays. And this is all roughly 4 times faster than the original algorithm, which is, again, sort of worth the effort. It's not 5% speed up by refactoring and complicating the code. It's a 4-fold speed up, which is hopefully for most users worth the effort. Even if I had to actually copy the data from the original array to x's, y's, and z's separately, and then copy all the results back, it might still be worth the effort because we're gaining so much speed by just doing vectorization here. Yes? Okay. Right. Another example from the same domain, which I'm not going to mull over for long, it's just another application of the same principle. This is n-body simulation. You have objects in 3-dimensional space, and you have gravity forces acting on these objects, right? They're applying forces to each other. So each particle or each object in your space has a mass, a velocity, acceleration, a bunch of a position, obviously, and you're trying to simulate their movement, which can be useful for anything, for computer games or actual space simulations. But again, the interesting thing is you probably have an array of structures. You have an array where each component is a particle or an object. And to vectorize, you would probably be better suited if you had a bunch of arrays with each component laid out sequentially. So instead of having a huge array where you have all the values for the first particle and then all the values for the second particle, you'd rather have an array with all the x's and all the y's and all the z's and all the velocity x's and so on. So you could operate on these arrays rather than the whole particle. I don't have the full vectorized code here. It's just another application of the same principle of converting from an array of structures, an array of particles here, to a structure of arrays, to a bunch of arrays with each structure's component individually laid out in memory. So it's a slightly different memory layout, which lets you speed things up. Okay, so I have 2 more examples which are not so mathematical or physical. These could actually be pretty useful in databases, for example, full-text search, queries, that kind of thing, indexing the web. Here we're trying to optimize strstr, which for C developers is pretty familiar. It's basically substring search. So the C# version, no frills, is just take a string and call contains. String has a method called contains, which finds if a string is a substring of that original string. So haystack contains needle. And then here's the vectorized version, which unfortunately we cannot yet express in pure C#. So what I did for the benchmark, I wrote it in C, and then the benchmark actually p-invokes, it does interop to call that version written in C. So we're paying for interop. And still, even though we're paying for interop, it is 9 times faster than the string contains method, which is hopefully implemented in managed code. So why is it so faster? What is this thing doing here? What is this code here with the really scary intrinsics like CMP, EQ, and load U SI to 56? The basic idea is illustrated here. I have my string over here. The quick black fox jumped off, and so on. I put black here because I wanted 2 Ks there. I know it's brown. And what I'm looking for, the string I'm looking for, is quick. Okay? So this is the haystack, the quick, black fox jumped, and so on. And I'm looking for the substring quick. So what I'm doing is I take a vector of characters and I fill it with the first letter of my needle, which is Q. And I take another vector of characters and I fill it with the last letter of my needle, which is K. So I'm looking for quick, so Q and K. And then what I do is I simultaneously compare my original string with this vector of Q's and this vector of K's at an offset. I know the string I'm looking for is quick, so I offset the K's by 5 from where the Q's start. That's all I'm doing, I'm just comparing. And then the result of that comparison is potential indexes where my substring could start. Wherever I found the Q in the original string, that could be a potential match. It doesn't have to be, but it could be. Wherever I found a K in the original string could also be a potential match. Not necessarily, it could be. If both of these match, if I found the Q and the K at the right distance from each other, it still doesn't mean it's a match, but it's a more likely potential match. So once I have that kind of candidate, I can now check the actual characters. I can now compare the U and the I and the C to see if I have what I needed. But first, we eliminated a lot of potential places in the string by doing this simultaneous comparison across multiple places in the string. So this is the basic idea of this vectorized version. This is what it's doing. The CMPU EQ EPI8 is comparing vectors of characters, vectors of bytes, and finding the places where they're the same. And then there's some work on extracting where exactly they are the same and figuring out that we need to take this quick here and compare it with the actual substring we're looking for. The result, again, is pretty impressive. It's a 9-fold speed up. So think about it. If you had a database query and your database could speed that up by 9 just by using vectorization, it would be pretty nice. So databases obviously would have some use for this kind of thing, especially for full-text search. Here's another example from a somewhat similar domain. Yes?
So I guess the question is, vectorization for stuff is so powerful. Is there a reason it's not already implemented that way in the .contains example?
So you're asking, like, why aren't there libraries that just use this under the covers?
Yeah, in this particular case, you mentioned .contains. These are features that have been in the CPU for very many years.
Yeah. So, right. So there's 2 answers to this. One is that obviously for some problems, there's going to be a library that does this internally, and you definitely should use that library rather than using my code or trying to come up with your own. Intel, in fact, have a nice library which is written in C that has a bunch of vectorized algorithms inside. So for example, for matrix multiplication, you would obviously reach to that rather than implementing your own. But some things are just so domain-specific that it would be unlikely to find a library that does that. Or maybe there is a library, but it's for Linux and it uses Perl as its interface, and you take the idea from there and just implement it yourself. This str thing, I have not come up with this myself. I just copied it from some C implementation I found, and it's pretty effective. So in some cases, it's really worth being able to write these things out yourself. Yeah. But whenever there is a library, yep, definitely reach out for it. So here's just one final problem, again from sort of a database space. You have 2 sorted lists of numbers, and you want to find the intersection of these lists. You want to find all the elements that are in both lists at once. So why is this relevant for anything? Think about it. Suppose you have 2 queries to Google or some database, 2 strings you're looking for, 2 search keywords, and then you have a list of results containing the first keyword, and you have the list of results containing the second keyword, and now you want to find all the overlaps. You want to find the terms, you want to find, sorry, the documents that contain both keywords, that contain both terms. So you have 2 sorted lists, not necessarily of the same length, and you're trying to find all the common elements. So this is an interview kind implementation. It's a typical interview question. It's a loop basically that has 2 pointers into the lists, and it advances the right one, and it finds all the overlapping elements. Think about it, nothing to see here. And then the vectorized version, again, requires C, because there's a particular instruction here which is not wrapped by the .NET library yet. Might be in the future, not right now. And this is the instruction CMP-ESTRM, which is essentially implementing set intersection for us. It takes 2 vectors of bytes or characters, whatever we prefer, shorts or ints, essentially any length, and it finds all the common ones. So in our case, for example, for the purpose of the benchmark, I assumed we're looking for shorts. So the actual data is shorts. I have a list of shorts here and a list of shorts there. So I'm comparing uwords, 2-byte elements. And this instruction just finds all the overlaps for me. And then it's just the work of extracting them. Essentially, there's some work here that has to shuffle the vectors around to find the actual overlapping elements, copy them over to the output, and then advance. Again, it's not so interesting, but the result is interesting. It's 4 times as fast as the original naive version, which you might have written in an interview. So again, if we have a way of taking 2 query results and finding the intersecting elements 4 times faster, I'm sure you'd sign up for that. So this is, again, a pretty nice application of vectorization to something that's closer to the real world than matrices maybe, or vector normalization. There's a bunch more examples like this, literally hundreds of algorithms that have vectorized versions today. You definitely don't have, in most cases, you don't have to come up with your own original work. You might find something and then adapt it to your needs, or convert or refactor the data you have so that you can apply a vectorized algorithm to that problem. And in some cases, you might not get like the most optimal result. You wouldn't get the theoretical maximum you're capable of extracting from your CPU. You'd get pretty close. You'd get 80% with 20% the effort. This is pretty respectable. Okay, so these were a lot of examples of vectorization, and I want to spend the next few minutes talking about slightly different areas in the CPU that we can be taken advantage of. And specifically, I have a few examples around the cache and memory subsystem that are also worth reflecting over. So first, this is a very general description of what happens in terms of the memory system and the cache when you access memory from core. This is supposedly a typical i5 processor, which has 3 levels of cache. So this thing here, the gray one, is the CPU socket. This is a single unit which you pay for and install on your system. And then it has 2 CPU cores inside. Each core has a level 1 cache, which is separate from the other cores, and a level 2 cache, which is also separate from the other cores. And these 2 cache levels differ by size and speed of access. Level 1 cache can be accessed in 4 CPU cycles. Now think about it. Modern processors have a clock speed of, say, 3 gigahertz. So 4 cycles is like a nanosecond and a half, maybe a little less. The level 2 cache has a latency of 10 cycles. So say 3 nanoseconds, 4 nanoseconds, something like this. And it's a lot bigger. Sorry, I didn't say, but level 1 cache is typically 32K on Intel i series processors, and level 2 is 256K. So it's bigger, but slower, considerably slower. And finally, level 3 cache in this design is shared across both cores. It's a lot bigger. It could be 16 megabytes, even more on more sophisticated CPUs, but it's a lot slower as well, so 40 cycles, for example. And finally, main memory, which, as you know, can be really big. You could have terabytes of RAM on a modern server. That is accessible in more than 100 cycles. So it's really a lot slower than all the different levels in the cache hierarchy. If you can get your data to fit in level 1 cache and repeatedly access the same information, repeatedly access the same elements, you could have up to 30 or 40 times better performance than if you have to constantly go to main memory. This is the main result. And even if you're only able to use level 3 cache repeatedly, and you don't have to go out to main memory, you could get a nice win of 3x or even more, depending on your main memory, indeed. Now, if you have more sockets, more actual CPU packages, you would have multiple level 3 caches, and then there's some more logic required to coordinate them, which is something I'll touch on shortly. So here's the first example where this is relevant. It's a pretty classic one, going back to matrix multiplication once more. This is one loop, and this is another loop, which implement the same algorithm exactly, except the inner loops are interchanged. Here, I'm going over j and then over k, and here I'm going over k and then over j. So it might look like just a simple renaming, nothing more, but it's not just renaming because it changes the pattern of access in the actual core of the inner loop. What happens in the first example is that one of my matrices, the matrix B, is accessed like this. I'm going over a single column of the matrix. Whereas in this version, that same matrix B is accessed like this. I'm going over a single row of that matrix instead. In fact, in this third version, I'm going over rows only. There's not a single matrix where I'm going over a single column in the inner loop. The result is not as impressive as a lot of things we saw before, but still pretty impressive, especially if you consider the following. In this example, when I benchmarked, just to make the benchmarks run a little faster, my matrices were just 512 by 512 matrices of floats. So a single matrix would be 1 megabyte, 3 of them together, 3 megabytes, and my level 3 cache on the processor I benchmarked this on, my level 3 cache is 8 megabytes. So all of this data was able to fit in level 3 cache. And still, by accessing memory in a better pattern, by accessing memory consecutively, we were able to use the higher levels in the cache hierarchy better. So we didn't have to go to level 3 all the time. We were able to find what we needed in level 1 or level 2 in more cases. And the result is almost a 2x speed up. Another example, which is pretty similar, so I'm not going to spend a lot of time on, is tiling. In a lot of cases where you have data that you need to access in some random patterns, it might be better, instead of accessing it in random patterns, to make blocks, smaller blocks, and work on these blocks. Because the smaller blocks might be able to fit in cache. And then you finish a single block which fits in cache, you move on to the next block which fits in cache, and so on, reducing again the number of full cache misses you have to do. We don't have a lot of time for this, so just take a look at this later. The performance difference, again, is pretty considerable in this case. And in this case, still, all my data fit in level 3 cache. So again, it's not the worst case result for main memory. Okay, so one final thing I want to touch on when it has to do with memory and cache is where this whole cache subsystem or the memory subsystem can become an actual bottleneck for your algorithm. So the first thing to notice is, in a lot of cases, after you apply vectorization and parallelization and a lot of these optimizations, you end up with something that's so fast that memory becomes the limiting factor. And here's one example from an actual project I was on. What we wanted to optimize was dot product, a pretty simple operation on numbers. You have a vector of floats, you want to reduce it down to a single float, dot product operation. And what we had is multiple versions that I benchmarked, and other than finding the fastest one, which we did pretty quickly using vectorization, we were able to, on a single core, without parallelization, to reach speeds of around 23 gigabytes of data read from memory. So we had lots and lots of these floating point vectors, and we were working at the speed of 23 gigabytes per second. Now, memory on that actual system, the channel between memory and the CPU, had theoretical peak bandwidth of 25.3 gigabytes per second. So if you're at 23 something, that's pretty much the theoretical limit of how fast you can fetch stuff from memory before you just stall and have to wait. And so this is on a single core. Imagine putting 4 cores to work. You'd very, very quickly run into the maximum theoretical limit that your memory system is able to give you. And this is, again, exactly what the Intel top-down method is for. You would then identify that you are typically backend bound. Your backend isn't capable of issuing more instructions. And then you'd see which component of the backend is busy, and you'd see the memory system, your load instructions are stalling. You're not able to read from memory quickly enough for your super optimized CPU algorithm to process your data. This usually happens in simple operations like adding numbers or doing dot products, multiplications. If you have more work, if your algorithm is more complex, you would typically not run into memory limits that quickly, but it does happen, and it's an important thing to keep in mind. You might sometimes run into problems when you optimize too much because memory can't keep up with your amazing optimizations. That's just another part of the system. And a final example, I was saying caches can sort of interfere with each other. So my final example has to do with cache coherence or cache invalidation. When you have multiple caches, and pretty much on every single system today, you have multiple caches on multiple processors or multiple cores at least, there's the chance data in the different caches will not match. You could have the same memory location in two different caches having a different value, which would be potentially disastrous. So there is a very sophisticated protocol between these different caches designed to keep things in sync. So you don't have disagreements between caches which value is correct for a single memory location. The way it works is the following. So suppose you have some value in both cores caches on your system. That value is then marked as shared. Once a core wants to modify that value, it marks it as exclusive, and it causes the other core to lose that value. This is called invalidation. I had the value in both caches, and then core 0 invalidates the value in core 1's cache. And then finally, core 0 can write and actually modify that value. The result then go out to main memory, and if core number 1 needs that result, it will fetch it back into cache. Now what's interesting here is that this whole thing happens not on the scale of a single integer or a single float. This happens on the level of cache lines. A single cache line is 64 bytes in modern Intel processors. So whenever you have to evict something from cache, you evict 64 bytes. And whenever you have to read something into cache, you read 64 bytes. And then what happens is you get false sharing. You get invalidation which was not intentional. It's not two cores accessing the same memory location. It's two cores accessing adjacent memory locations, which happen to be on the same cache line. And so this very simple example, again, we're not going to drill into all the details here. I have two versions of the same code. One, I have a certain function run in the background and update an element in a shared array of doubles. And this runs in parallel on multiple threads. Each thread is accessing a different double. Each thread is updating a different element in a single shared double array. Second version, almost the same, except each thread is working on a local variable, and only at the end it updates the shared global double array. The speed difference is pretty crazy, especially when you add many threads to the mix. The key result to see here are the red lines. This is the first version as you increase the number of threads. So you have one thread, it runs in 54 units. You have two threads, it runs in 53 units. You have four threads, it runs in 55 units. It's not getting faster as you add more threads. Whereas the second version speeds up linearly from 54 to 28 to 15, and it could probably speed up even more. The only reason for this difference is that in this version, you're accessing adjacent memory locations from multiple threads, and in this version, you're accessing a totally different memory location, and only at the end you have to sync the results up. This thing is causing lots and lots of cache invalidations, whereas this version is not. So this is a pretty known phenomenon, but you keep running into this in a lot of different areas. It's really hard to predict at times which things are going to be adjacent in memory, so which patterns of use could end up colliding on the same cache location and cause this performance problem for you. So again, there are tools for this, and this is my concluding thought. There are tools for this. I wanted to show you as many examples as I could, so I didn't drill into each one and formally showed you where the problem is exactly before optimizing. But Intel and AMD, which are the two major processor vendors for us, they have tools available for benchmarking applications and pointing out what the performance problem is from the CPU's perspective. In fact, Intel even have tools like the Threading Advisor and the Vector Advisor, which would tell you, so here's a loop you could improve by using vectorization, and here's a loop where you applied vectorization, but you didn't get the best performance out of this loop. You should work harder on this loop, and you will get even more. So there's tools available for this, most of them commercial, but there's also some free information you can get out of your system. Looking into the future, finally, we'll probably see even more complex systems, even more complex processors that we have to optimize for. For example, we might see systems where you have hybrid cores, you have faster cores designed for certain tasks, and slower cores which consume less energy, which would be dedicated to somewhat other tasks. So you'd have to think about scheduling work across cores. You have external processing units, for example, Intel, the 72-core monsters. They can be added to a system as external PCI cards, so you could add multiple processors to the system dynamically and then use them as external processing units. There's the GPU, which, again, we could spend the whole talk talking about how to optimize for the GPU, which also has a bunch of cores available for you to use for general purpose computation. So there's a lot of interesting stuff to look into if you're interested in low-level CPU optimization, optimizing algorithms like this. So all my examples are available here on GitHub, and the slides, if you want them, are over here on Dropbox. If you have any questions, I'll be happy to answer, but I do have to move off the stage for the next speaker. So really, I appreciate you coming. Thank you very much, and enjoy the rest of NDC. Thank you.